The Moon, a world that seems utterly dry. During the day, lunar temperatures rise above 100 degrees Celsius, hot enough to make water evaporate almost instantly. At night, they plunge below minus 170 degrees Celsius, freezing everything into silence. There is only one place where water can exist: craters that have never seen sunlight for billions of years, where temperatures drop below minus 230 degrees Celsius. Water exists as invisible traces that can only be detected by the most advanced instruments. So does the surface of the Moon truly contain water? Or is it hiding it in the most elusive way imaginable? Join us on a journey to unravel this mystery through the breakthroughs achieved by space agencies around the world. The Moon is the closest celestial body to Earth, located just about 384,400 kilometers away. Humans first set foot on it in 1969 during the Apollo 11 mission. More than 50 years have passed, and dozens of spacecraft have orbited, landed, and drilled into its surface. Yet even today, science cannot provide a precise answer. How much water exists on the Moon? On the Moon, there is virtually no atmosphere. Pressure is nearly zero. Temperatures fluctuate to extreme levels, reaching up to about 127 degrees Celsius during the day, enough to boil away any drop of water. But when night falls, temperatures can plunge to minus 173 degrees Celsius, a difference of more than 300 degrees Celsius that makes any form of water extraordinarily unstable. So, if water cannot remain stable, how could we possibly find it? On the Moon, water hides in forms that are incredibly difficult to detect. It is like seeing footprints in a desert, yet not knowing whether they were left by a human or shaped randomly by the wind. Even when spacecraft deliberately create impacts to dig beneath the surface and observe the material ejected, the results remain ambiguous. This has led many scientists to consider a compelling possibility. Water may exist, but in concentrations too low to be easily detected. You could be standing on a region that contains water and never realize it with the naked eye. And this is the central paradox. Water does not disappear, yet it does not appear in the way we expect. Adding to this, the Moon's surface is constantly bombarded by the solar wind, a stream of high-energy particles from the sunday. These particles can break apart water molecules, splitting them into hydrogen and oxygen. This means that even when water forms, it may be destroyed almost immediately. This creates a strange cycle. Water may be created, destroyed, and then formed again, continuously, yet never accumulating long enough to become clearly visible. And to uncover the truth, we must go further. a small metallic machine quietly descended onto the surface of the moon, its drill beginning to bore into the gray, silvery soil, centimeter by centimeter, penetrating a surface that had remained undisturbed for billions of years. And when the drill reached a depth of about 2 meters, it brought up something that could completely change how we understand the moon. Traces of water. It was 1,976. The Luna 24 mission, the final probe in the Soviet Luna program, carried out one of the most ambitious tasks of its time, drilling deep into the moon's surface and returning samples to Earth. When the spacecraft returned, it carried about 170 grams of soil from the Mare Crisium region, an ancient basaltic plain. A tiny amount, almost insignificant, but in science, sometimes even the smallest quantity, is enough to shake an entire hypothesis. Scientists began analyzing the sample with the highest precision available at the time. And then, an unexpected result emerged. About 0.1% of the sample was water. If water truly exists just a few meters below the surface, it would mean that the moon is not entirely dead, as we once believed. And most importantly, we may have already found water, but have not yet understood how it truly exists. In the years that followed, scientists began to shift their approach. Instead of relying solely on direct samples, they started searching for indirect evidence on a global scale, signals that could cover the entire moon, rather than depending on a single sample. In 2008, India's Chandrayaan-1 spacecraft entered orbit around the moon. It carried a suite of international instruments, including the Moon Mineralogy Mapper, or M-Cubed, an infrared spectrometer developed by NASA. Every molecule in nature has its own unique spectral signature. For water and hydroxyl, this signature appears clearly in the wavelength range of about 2.8 to 3 micrometers. When data from Chandrayaan-1 was transmitted back and analyzed, scientists observed something impossible to ignore. Across the moon's surface, especially at higher latitudes, there were absorption signals precisely at the wavelengths characteristic of water and OH. For the first time in history, we had direct evidence that water or water-related molecules exist on the moon's surface. But the data also showed that the strength of the signal changes throughout the day. This suggests an entirely new process, Water on the moon is not static. It is created, migrates, and then disappears, following a day-night cycle. A bold experiment was carried out. In 2009, NASA launched the L-Cross mission, Lunar Crater Observation and Sensing Satellite. The plan was to create a controlled impact into a permanently shadowed crater near the South Pole. An Atlas V rocket stage, weighing about 2.3 tons, was directed to strike the surface at nearly 2.5 kilometers per second. The impact created a new crater and ejected a plume of material rising kilometers into space. Close behind, the L-Cross spacecraft flew through that plume, using spectrometers to analyze its composition. Within the ejected material, instruments clearly detected the presence of water ice. Analysis showed that about 5.6% of the mass of the plume was water, an astonishing figure, especially considering that previous discussions had only involved parts per million. In addition, other volatile compounds were detected, including hydrogen, ammonia, methane, and carbon dioxide. If water exists at the poles in the form of ice, and on the surface in molecular form, then is it limited only to these special regions? Or is water actually present across the entire moon, but in a form we have never fully understood? In 1994, NASA's Clementine spacecraft conducted a unique radar experiment as it passed over the moon's polar regions. Instead of simply capturing images, it transmitted radar signals toward the surface and measured the reflected return. The results showed that certain areas, especially within permanently shadowed craters, reflected the signals in a way strikingly similar to water ice. For the first time, scientists had reason to believe that materials containing hydrogen, the key component of water, might exist within those dark regions. But everything truly escalated with the arrival of another mission. In 1998, Lunar Prospector was launched with a clear objective: to map the moon's chemical composition on a global scale. One of its most critical instruments was a neutron spectrometer, capable of detecting hydrogen by measuring how it slows down neutrons emitted from the surface. When cosmic rays strike the moon, they generate high-energy neutrons. If hydrogen is present in the soil, these neutrons are significantly slowed. By measuring this change, scientists can infer where hydrogen exists, even if it is buried beneath the surface. Data from Lunar Prospector revealed large concentrations of hydrogen at both lunar poles, especially at the South Pole. Not just isolated spots, but vast regions stretching across hundreds of kilometers. Models estimate that if all of this hydrogen exists in the form of water ice, the total mass could range from about 10 million to 300 million tons. Enough to support long-term human habitation, enough to transform the moon from a lifeless world into a strategic outpost for humanity. But is hydrogen truly water? Because chemically, hydrogen can exist in many different forms. It can be part of a water molecule. They could only indicate that hydrogen is present here, not that this is water. Some scientists believe that most of this hydrogen does come from water ice, buried within permanently shadowed regions. Water may be there, but in quantities too small, perhaps buried too deep. Or perhaps we are still looking at it the wrong way. One of the most ambitious experiments came from the Lunar Prospector mission itself. After completing its mapping objectives, in 1999, the spacecraft was deliberately guided to crash into a region near the Moon's south pole at a velocity of about 1.7 kilometers per second. The goal was clear: to generate an impact powerful enough to release water vapor if ice truly existed beneath the surface. Telescopes on Earth immediately turned toward the impact site. Yet the result revealed no clear detection of water vapor. This raised a critical question. Was the hydrogen observed earlier unrelated to water? Or did water exist, but in quantities too small to produce a detectable signal? Japan, through the Kaguya Selene mission in 2007, carried more advanced instruments with higher resolution. One of its objectives was to observe natural impact events when small meteoroids strike the moon's surface in order to detect ejected material that might contain water. High-speed cameras and optical sensors recorded multiple impact events. Yet once again, no clear evidence of water appeared. There were no characteristic absorption signatures of water. What was observed was only dry lunar dust. Returning to the physical conditions on the moon, If water exists at extremely low concentrations, only tens to hundreds of parts per million, then even a large impact would not be sufficient to produce a visible cloud of vapor. The amount of water released could be too small, dispersing almost instantly into space. There is also a more critical factor. Remote sensing instruments must operate under extremely complex conditions. Reflected light from the surface, background radiation, and cosmic noise. All of these can mask the faint signals of water. These failures were not an endpoint. On the contrary, they served as warning signals, forcing science to rethink its approach. This became one of the most surprising discoveries in the search for water on the Moon. In 2020, the Sophia Infrared Observatory, a telescope mounted on a Boeing 747 SP, flying at an altitude of about 12 to 14 kilometers to avoid most of the water vapor in Earth's atmosphere, conducted a series of observations focused on the Moon. The objective was clear: to detect molecular water in its pure form, without confusing it with hydroxyl as in previous measurements. Unlike earlier observations that relied on the 3 micrometer band, Sophia focused on a wavelength near 6.1 micrometers. This is a spectral region where only water molecules strongly absorb. The target area was the Clavius crater, one of the largest craters on the Moon. Located in the southern hemisphere, but not within a permanently shadowed region. Previously, scientists believed that water could only remain stable in permanently shadowed regions, where temperatures are low enough to preserve it as ice. At daytime temperatures that can exceed 120 degrees Celsius, any free water molecules would evaporate almost immediately. First, water may become trapped within the microscopic structures of minerals on the surface. Tiny pores only a few micrometers or smaller can act as miniature cold traps, where temperatures are lower than the surrounding environment, allowing water molecules to persist for longer periods. Second, water may exist within glass beads formed by micrometeorite impacts. This leads to a remarkable conclusion. Water on the Moon does not exist in just one form, but may persist in multiple hidden states, distributed across the surface. From cold, dark regions to intensely sunlit areas. You could be standing on a region spanning square kilometers where water is present, yet the total amount across that entire area might only equal a few small bottles of water. On the moon, water is nearly invisible, locked within structures that the human eye can never perceive. But if water can exist both in sunlight and in darkness, then what is its true nature on the moon? To answer that, science must go deeper into the microscopic structure of each grain of lunar dust, where the final answers may still be hidden. You move gradually toward the moon's south pole, a place where sunlight almost never reaches. Before you lie deep, shadowed craters, regions known as permanently shadowed areas. Because the moon's axis is tilted by only about 1.5 degrees, sunlight always strikes the surface at a very shallow angle. Now imagine standing at the edge of one of these craters. Above you is blinding light where temperatures can exceed 100 degrees Celsius. But step just a few meters down, and you enter an entirely different world, where temperatures drop sharply to around minus 173 degrees Celsius. And in some places even down to minus 230 degrees Celsius, colder than the surface of Pluto. Data from orbital spacecraft show that at the moon's south pole, there are hundreds of craters locked in permanent darkness. Some of these craters stretch tens of kilometers across. If even a small fraction of them contains water ice, the total reserves could reach tens or even hundreds of millions of tons. We believe these ice reservoirs exist, yet we have never directly seen them. No camera can clearly capture the depths of these craters, and optical instruments are nearly useless. What we have instead is indirect evidence, neutron signals, radar reflections, and subtle shifts in energy spectra. Even the terrain itself makes access extraordinarily difficult. The crater walls are steep, and the surface is covered in fine, powdery regolith that can easily collapse. Temperatures are so low that electronic equipment can fail in a very short time. Models suggest that the ice may be buried beneath layers of soil ranging from a few centimeters to several meters thick. And if it can be extracted, it would not only provide water for survival, but also serve as the key to producing fuel, hydrogen, and oxygen, opening the path to building a long-term human presence on the moon. Yet even when we have attempted to do this, the results have only deepened the mystery and sparked an even greater debate. On the moon, water does not exist in the way we are familiar with. It hides. For decades, when we think of water, we imagine something visible, something we can touch, flowing liquid, or at least solid ice. The clearest evidence for this picture comes from the Chang'e 5 mission, when lunar soil samples were returned to Earth and analyzed with unprecedented precision. Within those samples, scientists not only found water in minerals, but also discovered it embedded inside tiny glass particles known as glass beads. These particles range from just a few dozen to a few hundred micrometers in size, smaller than a grain of sand, and are formed when micrometeorites strike the lunar surface at speeds of tens of kilometers per second. Generating enough heat to melt material and then cool it almost instantly. What matters is not just the amount of water, but the mechanism by which it forms and persists. The solar wind, a continuous stream of protons emitted by the sun, collides with the moon's surface, which is rich in oxygen within silicate minerals. When protons combine with oxygen, they form hydroxyl groups, and under certain conditions, even water molecules. Some studies estimate that even just the top few centimeters of the surface could contain a total amount of water reaching hundreds of millions of tons when considered across the entire moon. Yet this water is not concentrated in any one place. It is so widely dispersed that it is nearly impossible to collect using conventional methods. Imagine standing in a vast desert where every grain of sand contains a single molecule of water. And this explains why, for decades, humanity has repeatedly failed to find it. How do you extract a resource that is not concentrated, not fixed, and constantly changing over time? A combination of extreme factors, each one alone enough to make water effectively invisible, and together, they nearly erase any clear trace of its presence. A free water molecule on the surface can be broken apart or escape into space within a very short time, ranging from seconds to hours, depending on temperature and solar radiation. This means water never has the chance to accumulate in a way that we can easily detect. But even when water does exist, its concentration becomes another barrier. Measurements from multiple missions show that across most of the moon's surface, water content ranges only from a few tens to a few hundred parts per million. about 100 to 400 parts per million. That means, in 1 ton of lunar soil, the amount of water may equal only a few hundred grams. This makes distinguishing true water from hydroxyl groups a major challenge, one that has persisted for decades. Not only that, but water on the moon is distributed in an extremely uneven way. Instead of forming a continuous layer, it is fragmented and dispersed across different regions, shaped by local terrain, lighting conditions, and environmental factors. Time adds another layer of complexity. Water on the moon is not a static resource. As a result, measurement depends not only on location, but also on timing. All of these factors come together to reveal a deeper truth. Water on the moon is not difficult to find because it is rare, but because it exists in a form completely different from what we are used to. It is this scattered and difficult to access distribution that has turned the measurement of its total reserves into a multidisciplinary challenge, requiring breakthroughs in spectroscopic observation technologies and autonomous robotic exploration. Yet beyond these technical barriers, every milligram of water discovered serves as a kind of fossil, preserving the history of interactions between the moon and the broader solar system. Decoding and mastering this precious resource is not merely a geological achievement. It is a critical key that will allow humanity to establish a sustainable presence, transforming this satellite into a strategic launch platform for journeys deeper into the universe. We detected an unexpected signal coming from regions billions of light years away from Earth. What exactly happened? In 1977, the WOW signal appeared for exactly 72 seconds, at the precise frequency of the hydrogen atom, and then vanished forever. More recently, fast radio bursts, or FRBs, have once again challenged every known law of physics. Some of these energy bursts are up to 500 million times more powerful than the sun, yet last only a few thousandths of a second, coming from regions of space billions of light years away. Even more dramatic is FRB 180916, which repeats on a perfectly precise mathematical cycle, exactly once every 16.35 days, without drifting by a single second. Are we listening to extreme natural phenomena, or are we in fact hearing the heartbeat of a technology far beyond human understanding? Let us step together into a journey to explore these mysterious signals, as what we are detecting challenges every known limit of energy and time in the universe. For most of history, humanity observed the universe with its eyes. In reality, the light visible to the human eye represents only about 1% of the information the universe emits. The rest exists as radio waves, infrared, ultraviolet, X-rays, and gamma rays, entirely invisible to our natural senses. The turning point came in the 20th century, when humans did more than just see the universe. They began to listen to it. Radio astronomy emerged from a very practical need: understanding and eliminating radio interference that disrupted communications on Earth. Yet in the process, scientists uncovered a shocking truth: the universe is anything but silent. Every direction in the sky emits radio waves, including faint signals that persist for millions of years. Some signals are extraordinarily powerful, but last only fractions of a millisecond. Some are steady, like a heartbeat, while others are chaotic, like a storm of plasma. As radio antennas began scanning the sky, the data they collected was not sound in the ordinary sense, but patterns, intensity, frequency, periodicity, and polarization. Through this approach, entirely new classes of objects were discovered: pulsars. Neutron stars rotating with such precision that their timing deviates by only millionths of a second were first identified as regular radio pulses. Black holes, which emit no light of their own, began to reveal themselves through radio waves and X-rays from the swirling disks of matter around them. Interstellar plasma, once thought to be thin and inert, turned out to be a complex dynamical system filled with shock waves and turbulent magnetic fields. Each discovery pushed the boundaries of astrophysics further. If the universe produces so many signals, where is the line between the natural and the anomalous? As instruments grew more sensitive, scientists were forced to confront an unavoidable reality: not every signal fits existing models. Some signals are far more powerful than their predicted sources should allow. Some are too regular in environments that should be chaotic. Others originate from distances so vast that the energy required to produce them seems to exceed every familiar scenario. Most importantly, these signals are not rare exceptions. They appear often enough to be impossible to ignore, yet different enough to resist easy explanation. The question was no longer whether a signal existed, but where it came from, what mechanism produced it, and whether our current laws of physics are sufficient to describe it at all. And from that foundation, one of the strangest discoveries of the 21st century emerged: enormous, perfectly shaped rings of radio waves, with no clear explanation. In 2019, within what appeared to be an otherwise familiar radio dataset, a shape emerged that rendered all prior experience meaningless. On deep radio maps of the sky, a nearly perfect circle appeared, with no clear emission core, no association with supernova remnants, and no match to any known astronomical structure. These structures were quickly named odd radio circles, or ORCs, which do not appear in visible light, exist only in radio wavelengths, and reveal themselves only when sufficiently sensitive telescopes survey a wide enough region of the sky. The instrument that changed the game was ASCAP in Australia. 36 dishes, each 12 meters in diameter, using phased array feed technology that allows simultaneous observation of roughly 30 square degrees of sky. Within the EMU project, ASCAP increased the number of detected radio sources from about 2.5 million to nearly 70 million. Their scale was immediately shocking, as ORC-1, the first confirmed structure, lies at a minimum distance of 1 billion light-years. Its estimated diameter is about 1 to 2 million light-years, more than 20 times larger than the Milky Way, while even the largest plasma bubbles produced by stellar explosions do not exceed a few thousand light-years. What makes ORCs even more puzzling is their symmetry, because if such a colossal explosion had occurred, a central remnant should exist. Observations with MeerKAT, one of the most sensitive radio telescopes in the world, detected an elliptical galaxy located precisely at the center of ORC-1 at a distance of roughly 5 billion light-years. One possibility is a shock wave produced by the merger of supermassive black holes, but current models indicate that such a signal would struggle to maintain a stable circular form over hundreds of thousands of light-years. A second hypothesis involves jets from an active galactic nucleus, AGN, observed nearly along the line of sight. In this scenario, relativistic plasma outflows could create ring-shaped structures as they interact with the surrounding medium. However, most observed AGNs leave behind clear bipolar lobes rather than isolated closed rings. Another scenario is a post-starburst shock wave, a phase of intense star formation that ends by expelling matter on enormous scales, but the energy required to generate an ORC is far greater than that of any known starburst. What stands out is that ORCs are extremely rare, and before they could be explained, another signal appeared, far smaller in scale, yet no less shocking. It was not a giant radio ring, but an object emitting regular pulses every 22 minutes, something that theory insists should be impossible. If odd radio circles left astronomers puzzled by their enormous scale, the next signal was shocking for the opposite reason. It was too regular, too stable, and existed in a region where theory says no radio emission should be possible at all. This object, known as GPM J183910, lies relatively close within our Milky Way, about 18,000 light-years from Earth, and emits radio pulses that repeat with clock-like precision every 21 minutes and 58 seconds. Each emission lasts between 30 seconds and 5 minutes, then shuts off completely, nearly 22 minutes later. It turns on again, right on time, never early, never late. According to standard theory, the dominant periodic radio sources in the Milky Way are pulsars, rapidly rotating neutron stars with periods ranging from milliseconds to a few seconds. Even the slowest known pulsar spins about 1,000 times faster than GPM J183910. A typical pulsar completes one rotation in roughly 1 second, while GPM J183910 would rotate at nearly 1,318 seconds per cycle if interpreted as a rotating object. This period places GPMJ 183910 deep within what is known as the pulsar death valley. In this regime, magnetic fields are too weak and rotation too slow to accelerate charged particles, making observable radio emission theoretically impossible. The first hypothesis considered was a magnetar, a type of neutron star with an extremely strong magnetic field, known to power some of the most extreme radio and gamma-ray phenomena, including fast radio bursts. However, magnetars are typically accompanied by intense X-ray or gamma-ray emission. A second hypothesis points to an extremely magnetic white dwarf. White dwarfs are roughly Earth-sized, but contain nearly the mass of the Sun, and in some cases possess very strong magnetic fields. A slowly rotating white dwarf could, in principle, produce radio pulses longer than those of a pulsar. Yet, to generate a signal as strong and as stable as GPM J183910, a white dwarf would require magnetic fields and emission mechanisms far beyond what current models allow. If so, GPM J183910 is not merely an oddity, but direct evidence that our inventory of compact objects in the Milky Way is still incomplete. Notably, GPM J183910 does not emit continuously, and its pulses last far longer than the millisecond flashes of pulsars or fast radio bursts. This suggests a mechanism that slowly stores energy, releases it, then enters a dormant phase. So why was it only discovered recently? Earlier radio surveys typically focused on short bursts or continuous sources, making them likely to overlook signals with periods of tens of minutes. GPM J183910 may have been broadcasting for thousands of years, but only with instruments like ASCAP and Meerkat. Combined with long-period search algorithms, did it finally reveal itself. And as science struggles to understand this impossible slow pulsing source within our own galaxy, far beyond it, even shorter, stronger, and more mysterious signals continue to appear, whispers lasting only milliseconds, yet carrying staggering amounts of energy. If the 22-minute signal from GPM J183910 left scientists confused because it exists where it should not, then fast radio bursts, known as FRBs, are staggering for a different reason. They are incredibly brief, extraordinarily powerful, and come from distances that seem almost unimaginable. FRBs are radio pulses that last only a few milliseconds. In that fleeting moment, a single FRB can release energy comparable to, or even greater than, the total energy emitted by the Sun over many days, and then it disappears. The first FRB was discovered in 2007 within old archival data, and at first, many scientists believed it was an instrumental error. But as additional FRBs continued to appear from different regions of the sky, all sharing similar characteristics, the truth gradually became clear. This was an entirely new cosmic phenomenon. What makes FRBs especially remarkable is their origin beyond the Milky Way. Analysis of the signal's dispersion shows that the radio waves have traveled through vast amounts of plasma in intergalactic space. This makes it possible to estimate the distances of many FRBs at billions of light years. Time is the critical factor, because a pulse lasting only 1 to 5 milliseconds requires the emitting source to be extremely compact. It cannot be a large cloud of gas. The emitting region must be no larger than a few hundred kilometers, otherwise the signal would be stretched in time. This immediately directs attention toward extreme objects, neutron stars, magnetars, or physical systems that have not yet been fully described. For more than a decade, FRBs remained an almost complete mystery until a major turning point occurred in 2020. For the first time, an FRB was detected within the Milky Way, and its source was identified as a magnetar, a neutron star with a magnetic field so powerful that it can distort atomic structures. This discovery strongly reinforced the hypothesis that at least a portion of FRBs have a natural origin. However, not every FRB is accompanied by X-ray or gamma-ray emission. In addition, the environments of many FRBs vary widely. Some originate from galaxies undergoing intense star formation, while others come from old, gas-poor galaxies where magnetars are rarely formed. This suggests that FRBs are not a single phenomenon, but a collection of different processes that produce similar signals. The sheer number of FRBs is also astonishing. Estimates suggest that thousands of FRBs may occur each day across the observable universe. They erupt constantly everywhere, but only a very small fraction are aimed toward Earth and fall within the field of view of our telescopes. In that sense, each FRB is like an ultra-brief flashlight, shining through the space between galaxies and revealing the invisible structure of the universe. After a cascade of strange signals from deep space, from gigantic radio rings, to regularly repeating pulses that defy theory, to radio explosions lasting only milliseconds, a question slowly emerges, not from the data itself, but from the silence. And it is a paradox bearing the name of Enrico Fermi. If the universe is so vast, if the laws of physics are universal, if life is not a rare occurrence, then why do we see no clear signs of other civilizations? Modern observations show that most stars host planets, and a significant fraction lie within zones where liquid water could exist. In the Milky Way alone, the number of planets with potentially life-friendly conditions may reach into the tens of billions. Meanwhile, humanity has been in the radio age for less than 120 years. But Earth's radio bubble, the region of space reached by our artificial radio waves, extends only about 60 light-years in radius. So if other civilizations exist, it is very likely they are confined within similarly small bubbles. But here is the problem. The universe is more than 13.8 billion years old. The Milky Way formed over 10 billion years ago. If even a single civilization had emerged just a few million years earlier than us, it would have had ample time to spread across the galaxy, even at speeds far slower than light. For more than half a century, humanity has been listening, and SETI has scanned millions of frequencies. The crucial point is that science does not suffer from a lack of signals. On the contrary, we are surrounded by countless natural sources: pulsars, fast radio bursts, interstellar plasma, and background radiation. But none show any sign of intentional communication. Many hypotheses have been proposed, with some suggesting that complex life is extraordinarily rare, and that Earth may be a statistical exception. Other hypotheses argue that advanced civilizations may not transmit in ways we are searching for. The Fermi paradox does not claim that there is no one out there. They may use technologies far beyond radio, or they may deliberately remain silent. In a universe filled with dangers, broadcasting powerful signals could be a risk. It simply states that we have not yet seen them, within an observational window that remains astonishingly small. And that humility is the foundation of science. The task, then, is not to search for messages, but to look for physical traces left behind in space. And among those traces, one quiet yet persistent signal is challenging our understanding: the excess of positrons detected near Earth. When people think about listening to the universe, we usually imagine radio waves, short bursts, repeating cycles, signals arriving from the depths of space. But the universe does not communicate only through waves. At a deeper, more subtle level, it leaves traces through particles. A positron is the antimatter counterpart of the electron. It has the same mass, but carries a positive electric charge. In physics, when an electron encounters a positron, the two annihilate each other, releasing energy in the form of gamma rays. According to classical models, high-energy positrons reaching Earth should be extremely rare. Yet in Earth orbit, at an altitude of about 400 kilometers, a particle detector has been quietly collecting data for years. As the dataset grew and precision improved, nearly 100 times greater than earlier experiments, the excess did not disappear. What, then, is producing this enormous number of positrons? Cosmic rays, primarily high-energy protons, can generate secondary positrons when they collide with interstellar gas. But the observed imbalance is too large to be explained by this process alone, forcing science to look toward more extreme sources. One of the leading suspects is the Geminga pulsar, a rapidly rotating neutron star located about 800 light-years from Earth. Geminga has a mass roughly 1.5 times that of the Sun, compressed into a sphere only about 20 kilometers wide. Spinning at high speed, it generates an intense magnetic field that continuously accelerates particles to enormous energies. Particle propagation models suggest that Geminga alone could account for about 20% of the excess positrons detected near Earth. That is a remarkably large contribution from a single source, yet still not enough to explain the entire phenomenon. What if it is not just one pulsar, but an entire population of old pulsars scattered throughout the Milky Way, quietly releasing positrons into space? Another possibility points toward dark matter, where particle annihilation or decay could produce high-energy positrons. But this hypothesis faces serious challenges. There are no sufficiently strong accompanying signals in other channels, and the dark matter models must be finely tuned to match the data. What this excess ultimately suggests is that particle acceleration processes in the galaxy, from pulsars and supernova remnants to interstellar plasma, may be far more complex than we once believed. The positron surplus reminds us that the universe has many voices. Some are loud, like fast radio bursts. Some whisper, like background radiation. And some are almost invisible, written in fundamental particles and extreme energy. To truly hear them all, science must expand its reach across every wavelength, every particle, every physical channel. And that is precisely the doorway to what comes next. A universe listened to across the entire spectrum, where telescopes and detectors together assemble a more complete picture of what is really happening in deep space. As mysterious signals continue to appear, science is compelled to listen to the universe with every sense it can muster. Not only with our eyes, not only through radio waves, but across the entire spectrum of energy and particles that nature allows. At the radio end of the spectrum, giant telescopes such as FAST, CHIME, MEERKAT, and ASCAP constantly scan the sky. FAST, with its 500-meter collecting dish, is the largest single-aperture radio telescope in the world, sensitive enough to detect extremely faint signals from tens of thousands of light-years away. CHIME, despite having no moving parts, surveys the entire northern sky every day, detecting thousands of fast radio bursts, more than all previous instruments combined. ASCAP and MEERKAT extend the story in a different direction with wide fields of view and high resolution. They map the shapes of enormous radio structures. These objects do not shine strongly in X-rays and leave no obvious traces in visible light. At higher energies, X-ray and gamma-ray telescopes track the most extreme processes: neutron stars, black holes, and violent mergers. These observatories reveal that many powerful radio signals are not accompanied by X-rays, as theory once predicted. That forces science to ask a difficult question. Are we misidentifying the objects we are observing, or is our physics still incomplete? Alongside electromagnetic radiation, particle detectors provide an entirely different layer of information. The AMS-02 instrument aboard the International Space Station does not listen to waves, it counts particles. It records electrons, positrons, protons, and other rare particles with unprecedented precision. Data from AMS-02 show that the universe does not only emit signals, it also disperses matter, particles carrying extreme energy, traveling across hundreds or even thousands of light years. When data from radio, gamma rays, and particles are brought together to process this enormous volume of information, science can no longer rely on manual observation. Astronomical big data becomes the central tool. Automated algorithms compare signals, filter out artificial interference, and determine whether a signal coincides with satellites, radar, or sources on Earth. Science is not searching for number sequences or alien Morse code. What researchers are seeking is physics itself. Particle acceleration mechanisms, magnetic field structures, the flow of energy through plasma, and the limits of current models. And yet, it is precisely within this complexity that science moves forward, not by leaping to conclusions, but by gathering enough evidence to understand just how much we still do not know. When confronted with strange signals from deep space, the natural human instinct is to look for a quick explanation. Yet over more than half a century of observing the universe through radio waves and high-energy radiation, not a single signal has ever been confirmed as artificial. There are no intentional repeating codes, no structures resembling language, no evidence of an extraterrestrial civilization attempting to communicate. This is not a failure of science, but one of its most important foundations. It forces science to remain faithful to data rather than to human desire. Signals such as odd radio circles, the 22-minute repeating radio pulses, or fast radio bursts are not explained by a single hypothesis. Each phenomenon opens multiple competing possibilities, and all must pass through the same rigorous process: independent observation, repetition, multi-wavelength comparison, and cross-verification using different instruments. If a hypothesis fails against the data, it is discarded, no matter how compelling the idea may seem. History offers a clear lesson. Pulsars were once suspected to be artificial signals when they were discovered in 1967 because their periodicity was so precise it seemed unbelievable. They were temporarily labeled LGM, Little Green Men, but only a few years later, as more pulsars were found, science understood them to be rapidly rotating neutron stars, an extreme state of matter previously unknown. Today, new signals are following a similar path, as existing models of neutron stars, magnetars, interstellar plasma, and environments around black holes have been remarkably successful in many cases. But when signals appear outside the allowed range of theory, such as an object rotating extremely slowly yet emitting stable radio waves for decades, science does not rush to label them unnatural. Instead, it asks a more difficult question. Have we fully described the physics under such extreme conditions? Sometimes it takes decades of data, millions of hours of observation, and collaboration across generations of scientists to move from "we don't understand" to "we partially understand." Science is also deeply cautious about coincidence. Every possible source of interference, from satellites and radar to Earth-based equipment, must be ruled out before a signal is considered genuinely astronomical. That is why, when a signal survives all these filters, its value lies not in how strange it is, but in the fact that it directly challenges the boundaries of what we currently understand. For decades, radio telescopes on Earth have recorded countless pulses emerging from the void, most of them originating from extreme physical entities such as neutron stars or fast radio bursts. However, when current mathematical models fail to decode a subset of anomalous signals, we are forced to acknowledge a gap in human knowledge. These signals are not merely streams of raw data. They are the lingering traces of immense energetic processes unfolding across distances measured in billions of light years. Their irregular and unpredictable presence serves as a reminder that the universe still operates through mechanisms far beyond traditional physical theories. Faced with this vast silence, filled with strange and persistent rhythms, science is no longer searching simply for the source of a sound, but for an answer to our place within a cosmos that has never stopped moving. The journey toward understanding is far from over, because with every signal we detect, we are reminded once again, the universe still holds countless secrets waiting to be named. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring